Hello everyone, in this video we're going to be looking at set theory. So we're going to be covering these objectives. At the end of this lesson you should know how to define a set, identify the various types of set, draw and label a Venn diagram, and illustrate various sets and subsets using Venn diagrams. So we start with the definition of a set. So when we're defining a set, it's a collection of well-defined, distinct objects. Distinct meaning they're different or they're unique objects. So the objects in a set, we refer to them as elements or members of the set. And when we are denoting a set, we use capital letters, and all the elements in the set are listed in curly brackets separated by a comma. So for example, if we define a set as vowels in the English alphabet, we can name that set. We've decided to call it set V. So notice we use capital V to represent the set. And so set V would be equal to A, E, I, O, and U. Now notice that each of the letters is separated by a comma and all the elements are enclosed in curly brackets. Now another type of set, we have the set of whole numbers between 0 to 8 exclusive. Now the word exclusive there is used to mean that 0 and 8 are not included as a part of the set. So only the numbers that are strictly between 0 and 8 will be considered. And those numbers would be 1, 2, 3, 4, all the way up to 7. So we decided to name that set W. So we use capital W, again, equal in curly brackets. All the numbers are listed and separated by commas. Now, when we are looking at the number of elements in the set, we also have a notation for that. So you will see something written as n of s equals a, and that is where the number of elements in set S equals some number A. So S is simply the name of the set and A is going to be some constant or some number. So if we're using the previous example, in set V we had 5 elements. So we would write n of V equals 5. In set W with the whole numbers, we had the first 7, well, not the first 7, but we had 7 whole numbers. So we would write n of W equals 7. And that is how we denote the number of elements in the set. So now that we know the basics of set notation, we can now start looking at the different types of sets. And first on our list is our universal set. Universe, the big set, right? Now the universal set is the set that contains all the elements of the other sets that may be presented in the Venn diagram, or essentially it's all the possible elements that we could consider whenever we're forming our set. Now the symbol that we use for the universal set is the U. There's also another symbol that we use that I will show you later on in this presentation. So let us think about this example that's given. So if set A is the set that contains the elements 1 and 2, and set B contains the element 2 and 3, then the smallest universal set that could contain sets A and B would be the set 1, 2, 3. So the universal set, as you can see, it contains all the elements that we needed to create sets A and B. Of course, there could be other definitions of universal sets that get much bigger. So we could have, for instance, the first 5 whole numbers or the first 5 counting numbers. We could define the universal set in several ways, but this is simply just the smallest possible universal set for those two sets there. Now the next set is our empty set or null set. And as the name suggests, the set is empty, it has no elements in it. So any set that doesn't contain any element, we call it the empty set, and we denote it using either of these two symbols. So the first symbol is the Greek letter phi, and it's written basically like a 0 with a line through it. And the next symbol that we use is just an empty pair of curly brackets to show that there are no elements in the set. So an example could be the set Z, which contains humans older than 300 years. Since there are no humans known to be older than 300 years, then the set Z does not contain any elements, And so you would write z equals to phi, or z equals the empty set of curly brackets. Now, the next type of set that we will look at is the finite set. Now, the word finite means it's limited, it has an end, right? So a finite set, it has a limited or a countable number of elements. The set starts somewhere and it ends somewhere. We can literally list all the elements of the set. So an example of a finite set could be the first four odd counting numbers. So this set will contain the elements 1, 3, 5, and 7. So since there's a finite number of elements or a countable number of elements, then set A is said to be finite. Now the opposite of a finite set is of course the infinite set. Now if a set is infinite, it means that it does not have an end. It's unlimited or it's uncountable. So for example, if we were considering a set B, which has odd counting numbers, then that set goes on forever and ever without any end. So the first few odd counting numbers are 1, 3, 5, 7, and 9, but we can list infinitely many more counting numbers that are odd. So this set would be an infinite set. Now the next type of set that you need to be familiar with are equal sets. Now, two sets A and B are said to be equal if they have identical elements, meaning they must contain the same exact elements. And we denote equal sets with just the equal sign, A equals B. So if we have two sets, for example, set P has elements 1, 2, and 3, and set Q has elements 3, 2, and 1. We can see that the elements, although they're listed in a different order, they're identical to each other. So all the elements in P are identical to all the elements in Q, and so P is equal to Q. Now, when we're talking about equivalent sets are sets that contain the same number of elements. So the elements don't necessarily have to be identical. You just need to have the same amount in each set for them to be considered equivalent. So if we have two sets, sets A and B, and the number of elements in A is equal to the number of elements in B, then the sets are equivalent. And we denote equivalent sets using this symbol here, which is basically the equal sign but with 3 bars, or we use the tilde to say that those two sets are equivalent, sorry. So here's an example. Set J has the elements 4, 5, and 6, and set K has the elements X, Y, and Z. So those two sets are equivalent because they have 3 elements in the set, right? Each set has 3 elements. Now it's important to note that whenever we have a set that contains repeated elements, the elements are only counted once. So for example, here we have set A equals PQR, QPR. So we can see that the letter P, Q, and R, they're all repeated twice in the set. But because we're only counting the distinct elements, remember that's how we described our set. It's a collection of well-defined distinct elements. There are only 3 distinct elements in set A, and those elements are P, Q, and R. So the number of elements in set A is actually 3. We don't count the elements that are repeated more than once. Same concept holds for set B. So the 2 is repeated twice and the 3 is repeated twice, but we're only going to count them one time because we're counting the number of distinct elements. So essentially the number of elements in both sets A and B is 3. And because they have the same number of elements, they're considered to be equivalent sets. Now for the next type of set, this is really a set relation. It's disjoint sets. And disjoint sets are sets that do not have any elements in common. So in other words, their intersection, which is basically where the sets overlap each other, their intersection is empty. So we denote disjoint sets using A intersect B equals phi. So this upside down U is the symbol for intersection, and it's speaking about where the sets overlap each other. You already saw the symbol phi, which means empty set. So this is saying to us that the set of elements in the intersection of A and B is empty. So another example, we have set A which equals 1, 3, and 5, and set B which has elements 2, 4, and 6. So we can see that set A is just the first three odd numbers, and set B is the first three even numbers. So of course, these sets are disjoint. You don't have any numbers that are both odd and even. So there would be no elements in common between sets A and B, and they're considered as disjoint set. Now this diagram that we see is the Venn diagram. And as you should observe, with our Venn diagram, if the sets are disjoint, then as we said, the circles that represent the sets do not overlap each other. There is nothing shared, and so the sets are drawn separately. Now, the next type of sets that we need to know very importantly are subsets. Sub means smaller, right? So set A is considered to be a subset of set B if every element that is in set A is also an element of set B. So basically set A is contained in set B. Now there are two symbols that we use to denote subsets. So this statement, both of them are read A is a subset of B, but we're going to learn about two types of subsets and distinguish between the actual meaning of those symbols. So I'll get back to that in a second. Now, a very important fact that you need to know is that the empty set is a subset of every set, and every set is also a subset of itself. So read that statement again. The empty set is a subset of every set, and every set is also a subset of itself. And that takes us to the two types of subsets. So we have two types of subset, which we refer to as the proper subset and the improper subset. Now, a proper subset is one that is not equal to the original set, meaning it contains fewer elements than what was given in the original set. But for an improper subset, this is a subset that is exactly equal to the original set, and that is where these two symbols come from. So this second symbol here is actually the symbol for a proper subset, so it is read more correctly as A is a proper subset of B, and the first symbol is the one for that can denote improper subsets as well, and it's read as A is a proper subset or an improper subset of B. So if A is equal to B, it's an improper subset, but if A contains fewer elements than B, then it's a proper subset. And I hope that distinction is clear. So when we are looking at subsets, we can actually work out the number of subsets that would be in a set. But before we get to that, let us look at the Venn diagram for our subsets. So if P has the elements A, B, and C, and Q has the elements A, B, C, D, E, then we see that P is in fact a proper subset of Q because it's a smaller subset and all the elements in P are in fact contained in Q. So if we're studying the Venn diagram, we can see that the subset circle is drawn inside the larger set that it's contained in. And that is how we can identify a subset Venn diagram. Now, to work out the number of subsets that we can form from a given set, we use this formula 2 to the nth power, where n is just the number of elements in the set. So if we're given a set, for example, B, which contains the elements 5, 10, 15, and 20, then we can see clearly that the number of elements in B equals 4. Now, to determine how many subsets we can create, we will find 2 to the 4th power, and that gives us 16. Now, when we're listing the subsets of a given set, there is a particular method that we use. So as we said earlier, the empty set is a subset of every set. So typically that's the first subset that we list. Next, we're going to list the singleton sets, or the sets that only contain one element. So if we're forming one element sets from set B, then we could form a set that contains 5, one that contains 10, one that contains 15, and one that contains 20. And those are all the one element sets that we can create. Next, we try to create our two element sets. So to do this, to ensure that we create all possible sets, we keep one element constant at a time and try to pair it with all the other elements. So starting with 5, I would pair 5 with 10, 5 with 15, and 5 with 20. So notice I keep the 5's constant. And once I've paired 5 with every other number, I move to the next element. So I'm going to keep my 10 constant and pair it with all the remaining elements. Please note that the 10 was already paired with the 5, so we don't need to pair that again. So we would pair 10 with 15 and 10 with 20. So 10 is paired with all other elements now, so we move to the next one, which is 15. And 15 is paired with 20. It was already paired with 10 and already paired with 5. So these are all the possible two element sets that we can create. So now we move to the three element sets. So again, we use the same concept. We're going to keep the first two elements constant and pair it with the remaining elements. So I would keep my 5 and 10 constant, pair 5 and 10 with 15, then 5 and 10 with 20. Now I move to the next pair of constant numbers. So I can pair 5 and 15. I can keep 5 and 15 constant. So I would pair 5 and 15 with 20. We would have clearly already paired 5 and 15 with 10. So now I move to my next two elements, which is basically 10 and 15. So I'm going to pair 10 and 15 with 20 since it was already paired with 5. And that should be all my three element sets. Everything else was already tripled, so we have no more three element sets. So the final set that we can create, the final subset that we can create is the set itself. So as we said earlier, every set is a subset of itself. So that's the final type of set that we can create here. And that would give us all 16 possible subsets that we can create from set B. So now we take a look at the Venn diagrams. Now for a Venn diagram is simply a graphical representation that uses circles to show us the relationship between two or more sets. And basically how we position the circles is what really denotes the various relationships that we can observe. So the first type of Venn diagram, probably the most popular type that you will see, is the intersecting sets. And we show intersecting sets using overlapping circles. So if the circles are overlapping each other, then it means that there is an element or several elements that are common to all the sets or that's shared between the sets. So that is why we say the sets are intersecting. Now, as we mentioned earlier, if the circles do not overlap each other, then that denotes a disjoint set. So those sets, they don't have anything in common, so the circles are drawn separate from each other. And the other type that we mentioned as well was the subsets. So if a set is a subset of another one, then that circle is going to be drawn inside the circle of the larger set. So those are the three main relationships that you will observe from your Venn diagram based on the position of the circles. There are other relationships that you can observe from the Venn diagram too. And to indicate these, we basically shade different regions of the Venn diagram. So we're going to be looking at a few of those relationships now. So the first such relationship is the union of the set. Now, when we're thinking about union of two sets, A and B, we're thinking about all the elements in A or all the elements in B or the elements in both A and B combined. So union, if you're forming a union, it means that you're combining two things, right? So the symbol for union, it's a U, somewhat similar to the universal set. So if you see A union B, it just means that we're combining all the elements of A together with all the elements of B. Of course, if there's a shared element, we only list it once in the union. So in this example here, set A is equal to 1, 2, 3, and set B is equal to 2, 4, 6. We can see that there is one element common to both sets, and that is the element 2. But we're only going to list it once in the union. So if we put these two sets together, then all the elements that's formed is 1, 2, 3, 4, and 6. And that is the union of the set. So if I pick any element at random from this set right here, I am guaranteed that that element is either going to be a part of set A, or it's going to be a part of set B, or it's going to be in both of the sets. So union is usually used with the keyword or. Now, when we're thinking about intersection, as we mentioned several times before, the intersection means where the sets overlap each other. So when we're finding the intersection of sets A and B, we're looking for elements that are common to both sets. So is that element in both set A and also in set B? And for intersection, we represent it using an inverted U. So this just means A intersect B. So using the same sets A and B, if A is 1, 2, 3 and B is 2, 4, 6, the only element that is shared between those two sets or is common to both sets is the number 2. So A intersect B would be equal to 2. Now if we're looking at this on a Venn diagram, this first Venn diagram here shows us A union B. So the area that is shaded, we can see that all of set A is shaded. Set A is the region that's bounded by this first circle, and all of set B is shaded. That's the region in the second circle. So together, we circle the two regions under consideration, and that gives us set A union B. Now, if we're looking for the intersection, it's where they overlap each other. So the only element in the intersection here is 2. Now the next type of relationship, very important one, is the set complement. So the complement of set A is just all the elements that's in the universal set, but not in set A. So everything outside of set A forms its complement. So this is denoted as A prime or A superscript C. Any of those two notations means complement. So if we have a universal set that contains the fruits apples, banana, cherry, mango, and pear, and set A contains the fruits banana and mango, then the complement of set A, which we're calling A prime, would be all the fruits not in set A. So the apple, the cherry, and the pear. And we can look at this on a Venn diagram. So as we said before, set A is everything that's contained in the circle labeled A. So set A contains only mango and banana. So everything else outside of set A, which is again shaded, would be a part of the complement of set A. So we denote it as A prime or A superscript C. So we're going to look at a few more shadings. So we just saw this one. So set A is the region bounded here within the circle labeled A. And so A complement is everything outside of that circle. Similarly, set B is the set that is bounded by the circle labeled B. So everything in that shaded region is a part of set B. So set B complement would be everything outside of the circle that's labeled B. Now, if we're looking at the intersection, again, the intersection is where the two sets overlap each other. So if I'm looking for the complement of A intersect B, then I'm looking for everything outside of that overlapping region. And that is why in this set here, everything except the overlapping part is shaded. Now there's another way of thinking about the complement of A intersect B, and I'm going to try to show you why it is so. So we have here that A intersect B complement can also be written as A complement union set B complement. So I'm going to shade both regions. So I'm going to shade A complement in red. So A complement is everything outside of the circle labeled A. So notice I'm shading everywhere outside of that circle. So all of this out here is A complement. Now I'm going to shade B complement in a different color, and with lines going in the opposite direction. So I'm going to shade it in blue this time. So B complement is everything outside of set B. So this is where I'm shading now. This is B complement. So I'm avoiding the circle that's labeled as B. Now, if I am looking for the union of those shaded regions, then it simply means that I'm going to be combining the shaded regions into one thing, right? So union means we're putting them together. So if I'm putting all the shaded regions together, you can see that the only place that is not shaded is this region up in here, right? So this is the only region that was left unshaded a while ago. So it means that everything outside of the intersection of sets A and B is a part of its complement. And so A complement union B complement is in fact equivalent to this expression. Alright, so let's try another one. So again, this is the union of sets A and B. We basically just shaded all of A, all of B, put it together. Now, if I'm finding the complement, then it means I want everything outside of that region. So everything outside is shown right here. And again, if we're using the same reasoning as before, we can see that A complement intersect B complement would in fact be the same region. So you can try this one on your own. You can shade the complement of set A, shade the complement of set B, and wherever they intersect or overlap each other, that is where your complement of the union would lie. Alright, so for the next one, this is just another summary. So we can see this small region shaded right here. But before we go any further, this is the symbol that I was telling you about earlier. This is the next symbol that we use to denote the universal set. It looks basically like a fancy E, right? So if we're looking at this region that's shaded right here, we refer to this region as A only. And to find this region, you can see that it's where set A intersects the complement of set B. So I'm just going to quickly do a little shade so you can understand what I'm saying. So if we shaded, for example, B complement, then we're shading all of this region outside of set B, right? Shading is not perfect, but you understand. So this is set B right here. Set B complement, sorry, shaded in green. And now I am going to shade set A in a different color. I'm going to shade it in blue. So set A is everything that's inside of this circle here. Now, if we're looking for the intersection of those two shaded regions, we see that it's the small part out here, right? So this part out here is where the shadings actually overlap each other. And so that right there is A intersect B complement. So A intersect B complement gives us the elements that are unique to set A. So it's elements in A that are not in set B. So going on to the next one, this is now B only. We can see that it's the elements that are unique to set B alone. So it's the elements that are in B that are not in set A. And again, we can describe this region as where B intersects A complement. For the next set, we can see that this is the complement basically of A only. Notice that only the elements that are unique to A are not shaded. And to find this region, we can think about it as the complement of set A, which is everything outside of set A, union the elements that are in set B. So everything outside of A, if we shaded A complement and we shaded set B and we put all the shaded regions together, then we get the union of A complement with set B, and that is what gives us the shaded region that's shown there. Now similarly again, if we were to find the union of set A with B complement, then we basically get all the elements that are we basically get all the elements that are in set A but not in set B, right? And everything outside. So that is how we ended up with that shaded region there. So you should be able to identify the set notation of the shaded regions and also vice versa. Now, the last thing that you need to learn in this lesson is set difference. Now, set difference, the difference of two sets A and B is denoted as A minus B, and it's essentially all the elements that are contained in set A but are not in set B. So in simpler terms, it's just the elements that are unique to the first set in the difference. And in this particular instance, it would be the elements unique to set A. So again, as we just mentioned, any element that is unique to set A alone is called A only. So we can denote A minus B as A intersect B complement because we're looking for the elements that are in A but are not in B. So here's an example. If we have our universal set, which contains counting numbers from 1 through to 6, and set A are the counting numbers from 1 to 3, and B are from 3 to 5, then A minus B would be the set 1, 2, because those are the elements that are in set A that are not in set B. Notice that 3 is also an element of B, so it would not be a part of A minus B. When you're thinking of A minus B, you can also read it as A without B. So anything that is in B that's also in set A would be removed, basically. And please note that order does matter. Just like with regular numbers where subtraction is not commutative, meaning you cannot switch around the order and get the same answer, the same thing holds with set notation. So A minus B will not give you the same thing as B minus A. B minus A is B only, whereas A minus B is A only. So what we have represented in this Venn diagram here is A only, all the elements that are in set A that are not in set B. So I hope you found this presentation quite useful and you understand set theory a little bit more. In the next video, I'm going to go through the solutions for the practice questions. So I hope that you will attempt them on your own and then watch the video to see if you got your answers correct. Thank you for watching.